There is a number in physics that most people never hear. 1.6 times 10 to the negative 35th meters. The Planck length. It is so small that the proton, the thing inside the nucleus of an atom, is 20 orders of magnitude bigger, 20 zeros bigger. And yet, this tiny number keeps showing up in physics in unexpected places. It is where general relativity stops working. It is where quantum mechanics stops working. It is where every modern theory of what spacetime is made of agrees that the current picture runs out. It is, in a quiet way, the address where every difficult question in physics keeps coming back to live. Get comfortable. Hit subscribe if this is your first time here, because by the end of this, you will know why the foundation of the universe ends at a number nobody can ever look past. Now, let's slowly ease into this. Part 1. The question that has no flaw. There is a question almost every child asks at some point, and almost every adult quietly stops asking. If I cut something in half, and then in half again, and then in half again, and I keep doing it forever, what do I end up with? At first the question feels almost playful. A piece of bread, a grain of sand, a drop of water. The pieces get smaller and harder to imagine, and somewhere along the way the question begins to feel less like a puzzle and more like a door. And you can stand in front of that door for the rest of your life without ever quite working out whether anyone is supposed to open it. Most of us walk away. Physicists, very stubbornly, did not. The ancient Greeks asked the same question with a slightly different vocabulary. Democritus, in the 5th century before the Common Era, proposed that the world was built out of indivisible units he called atomos uncuttable. He had no microscope, he had no instruments at all. He simply reasoned that if you could cut and cut and cut without end, then nothing was really anything, and the world could not be what it seemed to be. So there must, he insisted, be a smallest something, a wall to the cutting. An atom, the word in Greek, is built into the floor of the question itself. Uncuttable, end of the line, below this no more. Democritus was wrong about the details, of course. The thing he called an atom is not, in modern physics, an atom at all. The thing we now call an atom is, as it turns out, very cuttable. The thing inside the atom is also cuttable. The thing inside that is, depending on how you count, also cuttable. The Greeks had the right idea, but the wrong scale. They put the wall in the wrong place. We have, over the centuries, found the wall in many wrong places. Every time we found a wall, the next generation built a sharper instrument, and the wall turned out to be a door. For 400 years now, the entire experimental enterprise of physics has been, in one form or another, an attempt to keep cutting, to keep looking at something a little smaller than what we last saw, with a slightly better tool than we last had. The eye gave way to the lens to the optical microscope to the electron microscope to the synchrotron, and the synchrotron, eventually, to the kind of particle accelerator that wraps around a piece of farmland in Switzerland and is 27 kilometers in circumference. Every generation of physicists has stood, briefly, at what looked like the bottom of the ladder, and then a younger generation has come along, looked harder, and discovered that the bottom was just a landing. The atom looked indivisible until it wasn't. The proton looked indivisible until it wasn't. Every wall in the entire history of looking has eventually turned out to be a door. It is worth taking a quiet moment to honor the people who walked through those doors, because tonight we are going to walk the same staircase they walked, and we are going to walk it slowly. Robert Hooke, in the 17th century, draws a flea under his compound microscope and shocks the Royal Society with the structure of an insect's leg. Antony van Leeuwenhoek, around the same time, polishes a single lens by hand, and discovers an entire teeming microscopic world in a drop of pond water. 200 years later, Ernst Ruska builds the first transmission electron microscope and crosses the wavelength barrier of light itself using electrons, which are matter as if they were waves, which is a sentence that even now feels a little impossible. By the middle of the 20th century, physicists are using X-rays to map the atomic structure of crystals, and Rosalind Franklin, with one of the cleanest pieces of X-ray work ever done, is photographing the spiral lattice that turns out to be DNA. The descent down the ladder is not, in any of these stories, a triumph. It is a vigil. The people involved spent years preparing tools that almost worked, and then a few quiet minutes seeing what nobody had ever seen. Tonight, you and I are going to spend a couple of unhurried hours walking that ladder all the way down, not in a rush, not with any particular urgency about getting to the bottom. We are going to take each rung deliberately, because the strangeness of where we are headed only really lands when you can feel how far you have come. We are going to start at the surface, where what you can see is what light bouncing off it lets your eyes recreate, and we are going to descend with a kind of slow seriousness through the regime of microscopes, through the world of waves and particles, through the long blue line of accelerators, until we reach a place where, for the first time in the history of looking, the wall in front of us does not seem to be a door. This place has a name. It is called the Planck length, and it is roughly 1.6 times 10 to the negative 35th of a meter. If you wrote that out as a decimal, it would be a 0, a decimal point, 34 more zeros, and then a 1. That number is so small it is hard to even gesture at it. A single hydrogen atom is, compared to the Planck length, about as wide as the Earth's orbit around the Sun is compared to a single hydrogen atom. The proton, the thing inside the nucleus, is 20 orders of magnitude bigger than the Planck length. 20 zeros. To go from a proton down to a Planck length is to repeat the leap from the Earth's orbit down to a hydrogen atom twice over. If that does not quite land, let me try a different version of the comparison. Suppose you took the entire observable universe, roughly 93 billion light-years across, by current estimates, and shrank it down to the size of a proton. Then suppose you took a proton inside that shrunken universe and shrank that proton down by the same ratio again. The proton inside the shrunken universe is now, approximately, the size of one Planck length. You have nested 2 universes worth of scale inside the simple act of moving from a proton to the Planck length. The descent is not small, it is the deepest descent in physics. But what is far stranger than the smallness of the Planck length is what physics quietly says happens if you try to look past it. According to general relativity and quantum mechanics taken together, you cannot. Not because your tools are too crude, not because you have not been ambitious enough, because the very act of trying, the very thing that worked at every previous scale, all the way down from the optical microscope to the LHC at the Planck length, that act folds in on itself and stops returning answers. The microscope of the universe, used too aggressively, becomes a thing that hides what it is pointed at, and the hiding is not a flaw. The hiding is the rule. So, this is the question we are going to spend the rest of our time tonight with. Is there a flaw to reality? And if there is, what does it mean that we appear to have found it, but cannot stand on it? You are sitting in a chair right now, probably, or lying somewhere comfortable. The chair is made of something. The something is made of atoms. The atoms are made of quarks and electrons. The quarks and electrons are excitations of fields, and the fields live, supposedly, in spacetime. But at the bottom of all of that, where the Planck length lives, current physics literally cannot tell you what is underneath. The floor you are resting on, all the way down, ends in a question. Stay with that for a moment. The question is not whether anyone has worked out the answer yet. The question is whether the answer is, even in principle, something that anyone could ever work out. And we will spend the rest of this video walking, very gently, into the reasons why a growing number of physicists now believe the answer is no. Before we begin the descent, one quiet logistical note. The reason these arguments work, the reason any of this matters, is that they are not abstract, they are not philosophical. They are direct consequences of two of the most thoroughly tested physical theories ever written down. Quantum mechanics has been tested to absurd precision in every experiment ever set up to test it. The anomalous magnetic moment of the electron, predicted from quantum electrodynamics, matches measurement to about 12 decimal places. General relativity has, over the last century, been confirmed by gravitational redshift experiments, by light bending around the Sun during the 1919 eclipse, by the orbital decay of the Hulse-Taylor binary pulsar, by gravitational wave detections at LIGO and Virgo, by the recent imaging of black hole event horizons, by the Event Horizon Telescope. Both theories work. The Planck wall is what happens when you take both theories seriously simultaneously, in the regime where they cannot avoid each other. It is not a speculation about something that might be the case. It is what the most successful physics we have, applied honestly to its own logical conclusion, says happens. Tonight we are not making anything up. We are following the equations where they go. So pour another mug of tea, if you like, or settle a pillow, or close the laptop and just listen. The descent is going to be long, but it is going to be patient, and we have all the time in the world. There is no test at the end. There is just the wall and a few hours of slow walking between us and it. Part 2. How seeing actually works. Before we can talk about what it would mean to fail at seeing something, we have to talk about what it means to succeed. Because the act of seeing, which feels to you and me like the most natural thing in the world, is in fact a very specific physical process, and it has a very specific lower limit baked into it that nobody mentions in school. When you look at something, anything, your hand, your phone, a tree, a face, what is actually happening is this. A source of light, usually the sun or a lamp, is pouring photons into the room. Those photons hit the object. Most of them are absorbed. Some of them are scattered. A handful of those scattered photons happen to travel in the direction of your eye. They pass through the lens of your eye, they strike your retina, and your brain reconstructs from those few photons the picture that you experience as the world in front of you. The whole process, source, object, detector, is one continuous physical event. And because light is a wave with a definite wavelength, the process has a built-in resolution limit. You can only resolve features of the object that are at least as big as the wavelength of the light you are using. I want you to sit with that rule for a minute. Imagine a small wooden ship on a calm ocean at the end of a long, slow afternoon. The wind has picked up enough that long, slow waves are rolling underneath it. A wave passes under the ship that is much, much longer than the ship itself. What happens? The whole vessel just rises, gently, on the swell. Then it falls, gently, on the other side. The ship barely registers the wave at all, because the wave is too big to interact with anything that small. The hull is, from the wave's point of view, basically a point. From above, if you were a seagull, you would see the wave continue on across the water as if nothing had been in its way. The information about the ship is not in the wave that came out the other side. The wave never noticed. Now imagine the waves get shorter. They are now about the length of the ship. Suddenly, the ship matters. The hull scatters the wave, deflects ripples in every direction, and from the deflections you can, in principle, read off the shape of the hull. The wave has, finally, become a tool with which the ship can be seen, and the rule is symmetrical. Make the wave shorter still, and you can resolve not just the length of the ship, but the details of the hull, the shape of the prow, the lines of the planks, the notch where a rivet sits. The wave, made small enough, becomes a kind of finger that can trace the surface of what it touches. That is exactly the rule for light, and for every other wave in physics. To resolve a feature of size delta x, you need light with a wavelength at most about delta x. Anything longer, and the feature is too small for the light to notice. Anything shorter, and the feature is well within the resolution. There is a more careful version of the rule, involving Rayleigh's criterion and the numerical aperture of the lens, but at the level of what we need to do tonight, the simple version is enough. Wavelength is resolution. Longer than the feature, and the feature is invisible. Shorter than the feature, and the feature is visible. That is it. Visible light, the kind your eye uses, has wavelengths around half a micrometer, that is 500 nanometers. That is good enough to let you see hairs, cells, individual grains of pollen. It is not even close to good enough to see an atom. Atoms are around 1/10 of a nanometer across, which is roughly 5,000 times smaller than the shortest visible light wavelength. To see an atom, you need a wave whose wavelength is at least as small as the atom is. Visible light cannot do it. Even the very best optical microscope, the kind with oil immersion lenses, and every trick used, bottoms out at about 200 nanometers of resolution. That is the diffraction limit. It is the wall that light, as we usually use it, cannot get past. There are tricks. Stimulated emission depletion microscopy, super-resolution techniques, the kind of work that won the 2014 Nobel Prize in Chemistry for Stefan Hell and Eric Betzig and William Murnau. They can, with clever fluorescent labeling, beat the simple diffraction limit by a substantial factor, but they do not let visible light see atoms. They let visible light see structures a little smaller than its own wavelength by using the statistical fact that you can localize a point source very precisely, even with a fuzzy point spread function. The underlying physical rule that wavelength sets resolution is still in place. They have just been clever about how they use it. So you might think the answer is to switch to shorter wavelengths, and you would be right. X-rays have wavelengths in the range of about 1/10 of a nanometer, comparable to atomic spacing. Shine X-rays on a crystal, and the X-rays scatter off the regularly spaced atomic planes inside, and from the pattern of scattering, you can reconstruct the structure of the crystal at atomic resolution. This is X-ray crystallography, and it is, in essence, the same trick the ship and the wave are doing. We have just changed the wavelength of the wave to match the size of what we wanted to see. X-ray crystallography is, in a way that does not get enough credit in popular accounts of 20th century science, one of the most important techniques in the history of human knowledge. It is how we know what every protein in your body looks like. It is how we know the structure of hemoglobin, the protein that carries oxygen in your blood. It is how Watson and Crick, working from the X-ray photographs Rosalind Franklin had taken, deduced the double helix structure of DNA. It is, in a very direct sense, how we know what molecules are. Without the rule of wavelength and resolution, without the willingness to climb to a shorter wavelength and pay the energy price that comes with it, we would not know the inside of a single cell. There is a beautiful piece of symmetry buried inside the rule, which is worth noticing in passing. The same equation that tells you the minimum feature size you can resolve with a given wavelength also tells you the maximum wavelength a feature of a given size can produce when it scatters light. Resolution and emission are governed by the same wavelength. The reason a small antenna cannot broadcast a long radio wave efficiently is the same reason a long radio wave cannot probe a small antenna. The wave and the object have to be matched in size. The match is the whole physics. The asymmetry that exists in everyday life sources emit, detectors detect, objects sit in between, is a story we layer onto a deeper symmetry where the rule simply does not care which direction the wave is going. Now, here is a small detail that does not look important yet, but will become the whole story before the end of the night. Why does the rule work? Why is wavelength the resolution? At a very deep level, the answer goes back to a discovery Albert Einstein made in 1905, which is the next step in our descent. Part 3. Light is particles, and particles carry energy. In 1905, Albert Einstein took a problem that had been embarrassing physicists for years, the photoelectric effect, and solved it by proposing something that, at the time, sounded mildly insane. He said that light, which everybody knew to be a wave, was also, simultaneously, a stream of discrete particles. He called these particles light quanta. We now call them photons. The photoelectric effect, just so we are all on the same page, is this. Shine light on a clean metal surface, and the metal gives off electrons. The light is going in, the electrons are coming out. The energy of the light is being absorbed by the metal, and some of the electrons in the metal are being given enough energy to escape from the surface. So far, so classical. The strangeness was in the details. The classical wave theory of light predicted that brighter light should release electrons with more energy per electron, and dimmer light should release electrons with less energy per electron. That is not what happened. The energy of each released electron depended only on the frequency of the light, not on its brightness. Brighter light released more electrons. Dimmer light released fewer electrons, but each individual electron carried the same energy out, set by the frequency, no matter how bright the source was. Einstein's interpretation was that light, at the most fundamental level, was not a continuous wave handing energy out smoothly. It was a hail of discrete packets. Each packet carried a definite quantum of energy and a definite quantum of momentum. The energy of a single photon equals Planck's constant times the frequency of the light. Equivalently, since frequency times wavelength equals the speed of light, the energy of a photon equals Planck's constant times the speed of light divided by the wavelength. And here is the part that matters for us tonight. Because the energy of a single photon is inversely proportional to its wavelength, shorter wavelength light is automatically higher energy light. I want to say that twice, because the entire video is going to hang on it. Shorter wavelength means higher energy. To see smaller things, which requires shorter wavelengths, you automatically need higher energy photons. The rule of resolution and the rule of energy are not two separate rules. They are the same rule. Einstein won the Nobel Prize for this work in 1921. He did not, contrary to popular memory, win it for relativity. He won it for the photoelectric effect. The Nobel Committee found the photon idea so unsettling that they made sure to give the prize for the experimental fit, not for the radical underlying claim. The radical claim that light is genuinely particulate at its base took a long time to settle in. Even Einstein himself, in private letters years later, would say that he was not sure whether anyone had really understood what a photon was. So now we can write down something I am going to call, for the rest of the night, the master equation. To resolve a feature of size delta x, you need a photon of energy, at least about Planck's constant, times the speed of light, divided by delta x. Or, more compactly, the energy required is roughly hc over delta x. This little formula will travel with us all the way down the ladder, into the LHC, past the LHC, and into the region of the Planck length itself. Every time we ask how much energy it takes to see something a particular size, we are going to come back to this equation. It is, in a sense, the only physics fact tonight that you really need to keep in your head. Plug in some numbers. Planck's constant is roughly 6.63 times 10 to the negative 34th joule seconds. It is a tiny number. It is the fundamental quantum of action, the smallest unit, in some deep sense, that nature traffics in. To see a feature 1 micrometer across, you need photons with energy on the order of 2 times 10 to the negative 19th joules, which is about 1 electron volt. That is visible light. To see a feature 1 nanometer across, you need about 1,000 times more energy per photon, a kilo-electron-volt. That is the X-ray range. To see a feature 1/10 of a nanometer across, to resolve an individual atom, you need about 10 kilo-electron-volts per photon. That is hard X-rays. To see a feature the size of a proton, around 10 to the negative 15 meters, you need photons of about 1 giga-electron-volt. That is a billion electron-volts. That is the regime of particle accelerators. And to see a feature the size of 1 Planck length, you would need photons of about 10 to the 19th giga-electron-volts. We will come back to that number in a couple of hours. For now, just notice the shape of the curve. As you push delta x smaller, the required energy climbs without ceiling. The rule does not contain any "and then you stop." It just keeps going. The curve is logarithmic in the energy and the length both, which means each step down in size is a factor of 10 step up in energy. 8 orders of magnitude separate the wavelength of visible light from the size of a proton. 9 more separate the proton from 1 Planck length below. That is the rule we are walking down. The energy is the price of resolution. Every step deeper into the small is a step higher into the energetic. And that little detail, harmless looking on the page in front of you, is the seed from which the entire wall at the end of tonight grows. The rule does not, in itself, contain any warning. It just gets more expensive as you go deeper, and the universe waits, very patiently, for somebody to ask how expensive it can get before something fundamentally different happens. It is worth dwelling for a moment on the units. The electron volt is, in some ways, the natural currency of subatomic physics. 1 electron volt is the kinetic energy an electron picks up when it falls through a potential difference of 1 volt. Your phone battery is roughly 4 volts. The AA battery in a flashlight is 1.5 volts. The wall socket in a typical household runs at 110 or 240 volts, depending on which country you are in. These are all energies of order 1 to a few hundred electron volts per charge carrier. That is the scale at which chemistry happens, the energies that hold molecules together. The energies that pass between atoms when a flame burns. Walk up the energy ladder by a factor of 1,000 and you are at kilo-electron volts. That is the regime of X-rays. Walk up another factor of 1,000 and you are at mega-electron volts. That is the regime of nuclear physics, radioactive decay, fusion, fission. Walk up another factor of 1,000 and you are at giga-electron volts. That is the regime of high-energy particle physics quarks, the rest mass of protons, the inside of nucleons. Walk up another factor of 1,000 and you are at tera-electron volts. That is the regime of the LHC, of Higgs bosons, of the deepest current probes humanity has built. To go from there to the Planck energy is to walk up another 15 factors of 10. 15 orders of magnitude past the LHC. Every step on the ladder, in some honest sense, has had a Nobel Prize attached to it. The number of Nobels between us and the Planck energy is roughly the same as the number of Nobels between us and a household wall socket. Part 4. Matter is also waves. Now we add the second piece, and it is one of the strangest discoveries in 20th century physics, even though it is almost 100 years old at this point. In 1924, a French aristocrat named Louis de Broglie was working on his doctoral thesis. His older brother, Maurice, was an experimental physicist working on X-rays, and Louis had absorbed a lot of his brother's intuition that X-rays were both waves and something more particle-like. Louis had been thinking, in particular, about Einstein's photon. If light, which everybody had assumed was a wave, was also a particle, perhaps the symmetry ran the other way. Perhaps matter, which everybody had assumed was particles, was also, somehow, a wave. He proposed that every particle of matter, every electron, every proton, every whole atom, every whole molecule has an associated wavelength, given by exactly the same formula as for photons. Wavelength equals Planck's constant divided by momentum. His thesis committee found this so radical that they nearly failed him. They sent the thesis to Einstein for an opinion. Einstein, who knew radical ideas when he saw them, told them to give the man his doctorate. He wrote back that the work was, in his judgment, of fundamental importance and that it deserved to be taken seriously even if no one yet knew what to do with it. 3 years later, in 1927, 2 American experimentalists, named Clinton Davison and Lester Germer, working at Bell Labs in New Jersey, did exactly the experiment that would settle the matter. They fired a beam of electrons at a nickel crystal. If electrons were just little hard billiard balls, the beam should have scattered off the surface in a smooth classical pattern. Instead, the beam scattered into a series of bright peaks and dim valleys, a diffraction pattern exactly like the one X-rays make when they scatter from the same crystal. Matter was a wave. De Broglie was right. The Davison-Germer result is one of those small, quiet moments in 20th century physics that does not get enough attention. The experiment was, in some ways, an accident. Davison had been doing routine surface physics with an electron beam, and a small leak in the vacuum had let some air in and oxidized the nickel target. To clean it, they heated the nickel, which inadvertently grew a single, large crystal where there had been a polycrystalline surface before. The next time they ran the beam, the scattering pattern was completely different. It took them a while to realize they were looking at a quantum mechanical diffraction pattern, and not at a metallurgy artifact. By the time they understood, they had the cleanest possible confirmation of de Broglie's hypothesis on a laboratory bench. Matter, like light, was both a particle and a wave, both natures simultaneously, neither one going away. So now our toolkit doubles. We do not have to use photons to see small things. We can use any beam of matter we know how to make. Electrons, protons, whole atoms. Even, in modern experiments, whole molecules of carbon-60 buckyballs, 60 carbon atoms each arranged in a soccer ball pattern, fired through interference slits in a vacuum chamber, producing diffraction patterns at the other end. The carbon-60 experiments were done by Anton Zeilinger's group in Vienna in 1999, and they showed that even objects with hundreds of atoms still display measurable wave behavior. Each one carries a wavelength, given by h over momentum, and each one can in principle be used as a probe, in the same way light is used as a probe. This is exactly the working principle of the electron microscope. You take a hot filament. You boil electrons off it. You accelerate them through a potential difference, usually a few tens of thousands of volts. The faster the electron, the larger the momentum, the smaller the wavelength. By the time the electron has been accelerated to a reasonable laboratory voltage, its de Broglie wavelength is well below a nanometer sharp enough to image individual atoms. Modern transmission electron microscopes can resolve features below half an angstrom, which is well under the diameter of an atom. We are looking at individual atoms with beams of electrons, because each electron, by virtue of being matter, is also a wave. Aberration-corrected scanning transmission electron microscopes can now image columns of individual atoms in a crystal lattice, and the photographs they produce look, to the casual eye, like the kind of orderly dots you might draw in a notebook. Those dots are atoms. They are individual atoms. The instrument is doing what de Broglie said in 1924 it ought to be able to do. But there is one more refinement we need to make before we can keep descending. When particles get pushed to very high momenta, when the energy you have given them is enormous compared with their rest mass, the equations simplify in a particular way. The total relativistic energy of a particle is the square root of momentum times speed of light, all squared, plus mass times speed of light squared, all squared. When the first term completely dominates the second, The energy is just momentum times the speed of light, and the energy and the wavelength are related by exactly the same equation as for photons. Energy equals hc over wavelength. The electron, in this regime, is indistinguishable energetically from a photon. We call this the ultra-relativistic regime. What this means, practically, is that once we push past about a few hundred mega-electron volts of energy per probe, it does not really matter whether we are using photons or electrons. They behave the same. Our master equation energy roughly equals hc over delta x applies to both. For the rest of the video, when I talk about a probe, you can picture either light or matter. The wall at the end is not made of light. It is made of energy. And once we are in the ultra-relativistic regime, light and matter are just two different ways of paying the energy bill. That ability to use matter and light interchangeably as probes is, in some ways, the deepest single fact in 20th century physics. It is the place where the wave nature of matter and the particle nature of light fold into one another and become a single phenomenon with two faces. By the time we are working at the energies particle physicists work at, the distinction between light and matter is, for our purposes tonight, almost a vocabulary issue. The relevant thing is the energy, and what the energy lets us resolve, and what the energy starts to do when we push it too high. Hold on to this image of the wave inside the particle, and the particle inside the wave, because it is going to matter later. When we talk, in a couple of hours, about what kinds of objects can exist at the Planck scale, both string theory and loop quantum gravity will, in their own ways, take this wave-particle duality and extend it. The strings of string theory are, in some sense, the wave function taken seriously as a one-dimensional extended object. The spin networks of loop quantum gravity are, in some sense, the matter-wave concept extended to spacetime itself, where the network represents the quantum mechanical state of the geometry. Every modern theory of what is past the Planck wall is, in part, an extension of the dual nature of light and matter that we are walking through right now. The seed of the wall is in the seed of the rule. Part 5. Down to quarks. So far, every step of the way, the rule has been our friend. We push more energy into a probe. The wavelength gets shorter. We resolve smaller features. We see deeper. And every time we have done it, the descent has been rewarded with a new discovery. Visible light gave us cells. Electron microscopes gave us atoms. X-rays gave us the structure of DNA. The ladder of energy, pointed downward, has yielded one revelation after another. The first place this stops being a textbook exercise and starts feeling like a story is the year 1967 at the Stanford Linear Accelerator Center in California. SLAC, as everyone calls it. The setting is an unassuming piece of farmland near Palo Alto with a perfectly straight tunnel 2 miles long buried just below the surface. The tunnel houses a linear accelerator that takes electrons and shoves them in a precisely tuned electromagnetic ladder up to 20 giga-electron volts. By the standards of the year 1967, this is an unbelievable amount of energy in a single electron. To put it in some kind of perspective, 20 giga-electron volts is the kinetic energy that an electron would have if it had been accelerated through a potential difference of 20 billion volts. The lightning bolt outside your window during a thunderstorm tops out at a few 100 million volts. SLAC's accelerator was, in 1967, 100 times more potent than a lightning bolt, focused into a single electron, repeatedly, 24 hours a day. The beam hammers into a small target, first liquid hydrogen, then liquid deuterium, and what comes out is measured by a detector hall on the far side. The detectors of 1967 were not the cathedral-sized machines of the modern LHC. They were a series of magnetic spectrometers about the size of a school bus, designed to bend the trajectories of charged particles in a known magnetic field and read off from the curvature how much momentum each scattered particle had. The team would point the spectrometer at a given angle relative to the beamline and count electrons coming out at that angle for hours, building up the scattering distribution one event at a time. The team doing the measurement is led by three physicists named Jerome Friedman, Henry Kendall, and Richard Taylor. They were not looking for what they found. They were running what they thought was a fairly clean experiment to probe the size and the smoothness of the proton. The proton was, at that time, generally pictured as a slightly fuzzy charge cloud, a little ball of positive charge, spread out over about 1 femtometer. If you shone a high-energy beam of electrons at it, you should see a smooth fall off of scattered electrons as you went to wider angles, because the proton's charge would be more or less uniformly distributed. Robert Hofstadter had done elastic electron scattering off nuclei in the 1950s, had won the 1961 Nobel for the work, and had measured the smooth charge radius of the proton to be about 0.8 femtometers. The SLAC team was meant to be doing a slightly more energetic, slightly more refined version of the same kind of measurement. That is not what the detector saw. Instead, the team saw a substantial number of electrons coming out at very wide angles, with very high energy, far more than a smooth charge cloud could explain. The electrons were bouncing off something hard, something small, something point-like. The scattering distribution looked, in the words of the era, eerily similar to Rutherford's old alpha particle scattering off gold foil in 1909. The same telltale signature of small, dense scattering centers, hiding inside what had looked, from outside, like a smooth, uniform object. There was, inside the proton, structure. Not smooth structure, point-like structure. Something with edges, embedded inside something that did not look like it had edges. There is a photograph of the SLAC control room from this era. It shows a long bank of analog meters, oscilloscope screens, paper tape readers, and 1 or 2 researchers in white short-sleeved shirts looking down at clipboards. Nothing about the room looks dramatic. Nothing about the room signals that something foundational is happening. But on certain nights, in 1967 and 1968, in front of those banks of meters, the proton stopped being a fundamental particle. The shift in what humanity knew about the inside of an atom happened on quiet shifts at 4 a.m, with somebody on coffee duty bringing fresh paper tapes. The interpretation took years, and a lot of people had a hand in it. James Bjorken, at SLAC, did a lot of the theoretical work in 1968, and his student Richard Feynman, visiting Stanford that summer, watched the talk and immediately produced what became the Parton model, the picture of the proton as a bag of nearly free, point-like constituents that the scattering electrons were bouncing off. Murray Gell-Mann and George Zweig had already named the constituents theoretically several years earlier. Gell-Mann had borrowed the name from a line in James Joyce's Finnegan's Wake 3 Quarks for Mustermark, partly as a joke and partly because the constituents had been predicted to come in threes. By the early 1970s, the picture had settled. The proton was not fundamental. It had pieces inside it. The pieces, quarks, were real. The SLAC experiments were the first direct empirical confirmation that the proton has internal structure. In 1990, the Nobel Prize in Physics went to Friedman, Kendall, and Taylor for exactly this discovery. The energy ladder, once again, had been rewarded. By pushing electrons up to 20 giga-electron volts, we had cracked open a particle that, on its own, the entire periodic table had been built out of. There is a useful piece of arithmetic here, in case you want a quiet sense of how the energy and the resolved length connect. 20 giga-electron volts is 20 billion electron volts. Plugging into the master equation, 20 giga-electron volts corresponds to a probe with a de Broglie wavelength of about 6 times 10 to the negative 17th meters. That is 6/100ths of 1 femtometer. The proton, you will remember, is about 1 femtometer across, so the slack electrons were resolving features about 15 times smaller than the proton itself. Inside that resolution, 3 small dense centers were rattling around, the quarks, the pieces of the proton. By being able to look at distances about 1/10 the size of a proton, the SLAC team caught the proton in the act of being made of something. The energy ladder had revealed, once again, that the apparently fundamental was not quite. The rule held. Every wall had been a door. I want you to take a quiet moment with this. SLAC, the experiment, the team in the control room, the bewildered first reading of a scattering pattern that did not look the way the proton was supposed to look. The proton stopped being fundamental on a particular night in 1967 in a tunnel in California. The next morning, every textbook in physics was wrong. And the rule that had let them be wrong correctly until that night, the rule that pushing harder reveals more, was still the rule. The wall, again, had been a door. We had walked through. We had not yet, in 1967, met any wall that did not turn into a door. Part 6, the LHC, and where the numbers start to hurt. After SLAC, the energy ladder did not stop. It kept climbing. CERN's first-generation collider in the 1970s, the original SPS in the 1980s, then the Tevatron at Fermilab from 1987 onward, then, finally, the machine that everyone has heard of, even if they could not tell you what it does, the Large Hadron Collider, CERN, 27 kilometers of circular tunnel, buried about 100 meters under the French-Swiss border near Geneva. The LHC is, by any honest measure, the most powerful microscope ever built. It accelerates 2 beams of protons, in opposite directions, around its 27-kilometer ring, until each proton carries about 7 tera-electron-volts of energy. 7 trillion electron-volts. The 2 beams then cross at 4 collision points, where dedicated detectors the size of cathedrals, ATLAS, CMS, LHCb, ALICE record the debris of the head on collisions at a combined energy of about 14 tera-electron-volts. ATLAS, just to give some sense of scale, is a cylindrical detector 46 meters long and 25 meters in diameter, weighing about 7,000 tons. It is the largest particle physics detector ever built. CMS is shorter but heavier, packing 14,000 tons into a cylinder about 21 meters long and 15 meters in diameter, built around the most powerful solenoid magnet ever constructed at a particle collider. These instruments cost billions of euros and took decades of international collaboration to design and assemble. They are the instruments of a civilization that has decided, deliberately, to look as far down as it currently knows how to look. What does 14 tera-electron-volts buy you, in terms of our master equation? Plug in. The required photon energy to resolve a feature of size delta x is about hc divided by delta x. Solving for delta x, you find that 14 tera-electron-volts corresponds to a probe of about 10 to the negative 19th meters. That is 1/10,000th the size of a proton. The LHC is, when it runs, the only piece of technology on Earth capable of asking questions at that depth. And at that depth, things have been seen. The crowning achievement so far is the Higgs boson, announced on July 4th, 2012, at a packed seminar in the main auditorium at CERN. The Higgs boson is the briefly excited particle that lives in the field that gives mass to fundamental particles. The field is everywhere. The boson is a fluttering of the field, fragile and short-lived, and it took 50 years to find one. The LHC, at 14 tera-electron-volts, produces them at a rate of roughly 1 every several seconds during a good run. Each one decays in something like 10 to the negative 22nd seconds. The detectors do not see the Higgs directly, they see the decay products. From the decay products, they reconstruct, particle by particle, the brief existence of the field's ripple. The story of how the Higgs got found is worth pausing on, briefly, because it tells you something about the rule we are walking down. Peter Higgs and Robert Brout and François Englert and Gerald Guralnik and Carl Hagen and Tom Kibble and a few others, whose names usually get dropped from the standard shortlist, proposed the mechanism in 1960. The theoretical picture had to wait almost 50 years for the experimental apparatus to catch up. Nobody in 1964 had any idea what the mass of the Higgs would be. The standard model gave it as a free parameter. It could have been anywhere from a few giga-electron-volts to a few tera-electron-volts. The Tevatron at Fermilab spent years pushing up to 2 tera-electron-volts of collision energy and found hints but no clear signal. By the time the LHC switched on in 2009 and ramped up over the following 3 years, the mass of the Higgs was effectively the most expensive unknown number in physics. The discovery, when it came in 2012, came in at 125 giga-electron-volts. A factor of 2 below what the Tevatron could have seen on a good day, a factor of 112 below the LHC's full collision energy, right in the sweet spot. The Higgs had been waiting for us to be patient enough to look in the right place. This is what humanity can do, right now, with its best technology. We can produce the ripples of the field that gives mass to matter. We can resolve features 1/10,000th the size of a proton. We can pour 14 tera-electron-volts into a single head-on collision and watch what comes out. By any earlier century standards, this is magic. It is also, and this is the part that begins to hurt, almost nothing. Because the next step on the ladder is the Planck energy. Not the Planck length, yet just the energy required to probe it. The Planck energy is around 3 times 10 to the 19th giga-electron-volts. That is 10 to the 15th times larger than the LHC's collision energy, 1,000,000 billion times more energetic per particle than the most powerful machine on Earth. You can ask, idly, what kind of accelerator we would need to build to reach this. The LHC accelerates protons to 7 tera-electron-volts in 27 kilometers. If you scale the energy linearly with the size of the machine, which is, very roughly, how these things work, to reach the Planck energy, you would need an accelerator with a circumference of about 4 times 10 to the 16th kilometers. That is roughly 4,000 light-years across. The Milky Way is about 100,000 light-years across. We are talking about a machine a few % of the diameter of an entire galaxy. Let that sit. Not 100 kilometers long, not 1,000, not 1,000,000. 4,000 light-years. The nearest star to the Sun is 4 light-years away. To build a Planck energy accelerator on the same engineering principles as the LHC, you would need a machine extending from here roughly 1,000 times farther than the nearest star. The collisions, when they happened, would take light-years to travel from one side of the machine to the other. The detectors, if you built them, would record collisions whose signals had been in flight for longer than the entire history of agriculture by the time they arrived. There are other natural sources of high-energy particles. Cosmic rays bombard the atmosphere of the Earth at all energies, all the time. The highest energy cosmic ray ever recorded, nicknamed the Oh My God particle, was detected by the Fly's Eye Observatory in Utah in October 1991. It came in at about 3.2 times 10 to the 20th electron-volts. That is roughly 50 joules of kinetic energy in a single subatomic particle, the same energy a fast-pitched baseball carries, concentrated by Lorentz transformation into a single proton-sized object traveling at almost exactly the speed of light. It is the most energetic single particle anyone has ever caught. And it is still, in our master equation, about 8 orders of magnitude below the Planck energy. The universe itself, at its most extreme, is still nowhere near the energy required to probe one Planck length head-on. That is not an engineering problem. Let me say it once now, because we are going to come back to it later, with full weight. The wall in front of us, the wall we are walking toward tonight, is not a problem we can engineer around. Part 7. Pushing further and meeting a new player. So suppose, for the sake of argument, we ignore the engineering. Suppose, in some hypothetical world, with infinite patience and infinite funding, we kept building, kept scaling, kept pushing. Suppose we did not care that the machine would be a few % the size of a galaxy. Suppose we just kept feeding more and more energy into smaller and smaller probes, the way the rule says we should, and we kept looking to see what we resolved. For most of the descent, this works. We have already done it, generation after generation, all the way down to the LHC. The rule has been a friend. Push more energy in, see smaller things. But there is a player who has been waiting quietly in the wings the entire video, and I have not introduced them yet, because they do not matter at any of the scales we have looked at so far. Their name is Albert Einstein, again, but this time in 1915, with general relativity. General relativity says, in a sentence, that energy curves spacetime. Not just mass energy. Mass is one form of energy, and so massive objects curve spacetime, which is what we feel as gravity. But every other form of energy curves spacetime too. The kinetic energy of a moving particle curves it. The electromagnetic energy in a beam of light curves it. The energy content of a photon, yes, even a single photon, produces a tiny, tiny, tiny gravitational pull on whatever else is nearby. At everyday energies, the effect is so small you can ignore it forever and your equations will not notice. At LHC energies, the effect is still small enough that you can ignore it. At Planck energies, you absolutely cannot. This is where the entire video changes character. Up until this point, gravity has not been in the room. We have been talking about quantum mechanics, about photons, about wavelengths and momentum and Einstein's photoelectric effect. Gravity has been off in the corner, being responsible for, planets and stars, and the fact that the chair you are sitting in does not float to the ceiling. It has not entered the conversation. Gravity is, at human scales, the weakest of the 4 forces, by an enormous margin. The gravitational pull between 2 electrons is about 10 to the negative 42 times weaker than the electromagnetic repulsion between them. You can run a particle physics experiment for the entire history of the experiment without measuring a single gravitational interaction inside the detector. Gravity is, at the scales physicists usually work, irrelevant until you push the energy density high enough. Then it shows up, and once it has shown up, it does not leave. The way gravity announces itself in this regime is not subtle. It arrives, and it immediately takes over, and the previous rules of the game are not, strictly speaking, abolished, but they are now playing on a stage that is curving under their feet, and the curvature is what controls the outcome. The other 3 forces, electromagnetism, the strong nuclear force, the weak nuclear force, keep doing what they always do, but they do it on a background that gravity now sets. The conductor changes. The orchestra is the same. The music is, very gradually, going somewhere new. Here is what happens. To resolve a smaller feature, our master equation says we have to concentrate more energy into a smaller region. Energy density rises. General relativity says energy curves space. The more concentrated the energy, the more curved the space around it. At some point, the curvature becomes so extreme that the region of space we were trying to look at collapses in on itself behind an event horizon and forms a black hole. I want to give that a moment. The rule that has helped us all the way down the ladder from optical microscope to LHC contains within itself the seeds of its own destruction. Push hard enough, and the rule turns around and eats the very thing it was supposed to reveal, not gradually, not asymptotically. There is a particular scale at which the energy required to see a feature of a given size is exactly the energy at which that region of space collapses into a black hole. Below that scale, the harder you push, the bigger the black hole, the more of the surrounding space disappears behind the horizon, and the less you see. You are not seeing smaller, you are seeing less. This is the structural climax of the night. The act of trying to look closer creates the very thing that hides what you were trying to look at. There is something profound and a little bit beautiful about this. The universe is not refusing to be looked at by accident. It is refusing to be looked at as a direct consequence of the same laws that have been helping us look this far. The rule is built to break itself at a particular scale, and the breaking is the rule. Imagine, for a moment, the idealized version of the experiment. You are an experimentalist on a long, lonely, infinite night, conducting the cleanest possible microscope run anyone has ever done. You have a probe of unlimited energy. There is no cost. There is no engineering. There is just the dial in front of you and the screen showing what your probe currently resolves, and a small region of empty space in the center of your laboratory where the experiment is happening. You crank the energy up, the dial turns, the screen sharpens. The features you can see get smaller. You go past the atomic scale, the screen still sharpens. You go past the nuclear scale, the screen still sharpens. You go past the LHC scale, the screen still sharpens. You go 10 orders of magnitude past the LHC scale, the screen still sharpens. Then, without warning, without any change in the rule, without any signal that anything has gone wrong, the center of the region of space you were trying to see darkens. An event horizon forms around it. You can see the edge of the horizon. You cannot see inside. The horizon, on your screen, is a small black disk against a faintly textured background. You stare at it. You reach for the dial. You crank the energy higher. The disk grows. The harder you push, the bigger the horizon. The more of the surrounding space slides behind it. The image on your screen does not get sharper. It gets darker. You are not seeing smaller. You are seeing less. You stand there with your unlimited energy, watching the very thing you were trying to see hide itself, perfectly, behind a wall the universe just built out of your own probe. The wall is not made of nothing. It is made of you. The harder you push, the more thoroughly the wall closes. For a long time you stand in that laboratory, watching the dark disk on the screen. The light in the room is low. The instruments hum. The dial in your hand has rotated past every reading any human accelerator has ever reached. The room is quiet. There is no one to call. There is only the screen and the disk and the sound of the cooling fans. You have hit the wall. The wall is not a door. The wall, as far as you can tell, is part of the building. Notice, in this thought experiment, that the wall did not announce itself. There was no error message. There was no instrument failure. The probe was operating exactly as designed. The screen was displaying exactly what the screen was supposed to display. The dial was responding exactly as the dial was supposed to respond. Nothing went wrong in any technical sense. Everything went right. And the right behavior of everything in your laboratory produced, at a certain scale, the disappearance of the very thing the laboratory was designed to see. This is the strangeness that makes the Planck wall qualitatively different from any previous limit. Every previous limit announced itself. Diffraction limits show up as a known fuzzy edge on a microscope image. Detector saturation shows up as a flat line on an oscilloscope. Sensitivity limits show up as noise overwhelming signal. They all behave like limits. They all tell you when you have reached them. The Planck wall does not. The Planck wall is the moment when the universe, very calmly, draws a curtain across the part of itself it does not want measured, using the same physics that has been letting you measure all the way down to that moment. It is the most polite refusal in the history of physics. You did everything right. The universe simply, gently, will not let you see. Part 8. The Planck length, derived once. Now let us actually do the calculation. Not in any rigorous way, for that you would want a textbook, but at the level of dimensions and orders of magnitude that everyone in physics uses when they want to get a sense of where a scale lives. We have the master equation. The energy needed to resolve a feature of size delta x is about Planck's constant times the speed of light divided by delta x. We have, from general relativity, the Schwarzschild radius, the radius at which a given amount of energy or mass becomes a black hole. The Schwarzschild radius corresponding to an energy E is about GE divided by the speed of light to the fourth power, where G is Newton's gravitational constant. For reference, just so the formula has some flesh on it, Newton's gravitational constant G is about 6.67 times 10 to the negative 11th. In units where mass is in kilograms, and distance is in meters, and force is in newtons. It is, in absolute terms, the worst measured fundamental constant in physics. The uncertainty on G is about 2 parts in 100,000, far worse than any other constant of nature, because gravity is so weak at laboratory scales that the experiments are very difficult to do cleanly. People have been trying to pin G down to better precision for 2 centuries, and the residual uncertainty has stubbornly refused to shrink. That is a story for another night. The question we want to ask is, at what size delta x does the energy required to resolve it become exactly enough to form a black hole around that very region? In other words, at what delta x does the Schwarzschild radius corresponding to the required energy equal delta x itself? Set them equal. The Schwarzschild radius equals delta x. Substitute in the master equation for the energy. After a couple of lines of algebra, the delta x squared comes out as g times Planck's constant divided by the speed of light cubed. Take the square root. You are left with delta x equals the square root of gh over c cubed. That is the Planck length, about 1.6 times 10 to the negative 35th meters, using the reduced Planck constant. About 4 times 10 to the negative 35th meters if you use the unreduced version. Either way, it is 20 orders of magnitude smaller than a proton. The energy required to reach this length is, by the master equation, about 10 to the 19th giga-electron volts. That is the Planck energy. It is roughly the kinetic energy of a fully fueled car at highway speed, but packed into one single particle. The temperature corresponding to this energy is around 10 to the 32nd Kelvin, what physicists call the Planck temperature. The density of energy required to do it is around 10 to the 96 kilograms per cubic meter. These are the Planck units. Max Planck himself derived them in 1899 by asking what combinations of 3 fundamental constants, Newton's g, the speed of light c, and what would become his own constant h, give units of length, time, mass, and temperature. He was not, at the time, trying to find a smallest distance. The smallest distance interpretation came later, after general relativity and quantum mechanics were both in the room, sharing the same chair, having a conversation neither of them quite wanted to have. There is one Planck unit I have not mentioned yet, because we did not need it earlier, but it is worth dropping in now while we are taking inventory. The Planck mass. It is the mass at which a particle's reduced Compton wavelength becomes equal to its own Schwarzschild radius. You can derive it the same way we just derived the Planck length, by setting those 2 scales equal. The Planck mass works out to about 22 micrograms. That is, by particle physics standards, an enormous mass 20 orders of magnitude bigger than the mass of an electron. By everyday standards, it is the mass of about one flea egg or a single grain of fine sand. Nothing remarkable. Until you remember that this is the mass at which a single particle becomes its own black hole. Concentrate the mass of a flea egg into a region smaller than the Planck length, and you have made a Planck mass black hole. The masses in our world are extremely far away, in either direction, from the scale at which quantum mechanics and gravity become equally important on a single particle. The Planck mass sits in the middle. What you should feel about the Planck length is two things at once. First, it is small, 20 orders of magnitude below the proton, far below anything any human technology has ever come close to. Second, it is unreachable. Reaching it would require an accelerator a few % of a galaxy across, and even if you built that accelerator, the experiment you ran with it would, by the same physics, produce a Planck mass black hole about 22 micrograms of mass, concentrated into one Planck length of space, rather than a measurement of anything below that scale. The wall is not a problem we can engineer around. We are starting to feel the weight of that sentence now. The first time I said it, in the middle of talking about the LHC, it was just an aside, a snippy little remark about cost. The second time, after we walked through the black hole argument, it has changed. It is not about the accelerator. It is about the laws of physics being arranged in such a way that the experiment, even if it could be performed, would not return the answer it was designed to return. The wall is structural, not financial. There is something deeply unusual about that in the long history of science. Almost every limit science has previously encountered has turned out to be financial or technological in some sense. The neutrino was undetectable in the 1930s because nobody had a tank of water big enough, buried deep enough. Once Cowan and Rines built one at the Savannah River nuclear reactor in 1956, neutrinos were detectable. The gravitational wave was undetectable in 1916 because nobody had a 4-kilometer laser interferometer. Once LIGO built 2 of them, plus a third one at Virgo in Italy, gravitational waves were detectable. The molecular structure of DNA was unobservable in 1940 because nobody had the X-ray photographs at the right resolution. Once Rosalind Franklin took photograph 51, DNA's molecular structure was observable. All of these limits yielded to the same simple recipe: build something bigger, build something more sensitive. Wait, look. The Planck limit does not yield to that recipe. Even with a galaxy-sized accelerator, the experiment would, by the same physics, produce a black hole instead of a measurement. The wall is built into the recipe itself. This is why physicists, when they encounter the Planck wall in their own work, tend to handle it with a kind of religious carefulness that is rare in the field. It is not just another open problem. It is the place where the open problems generate themselves. Quantum gravity, dark energy, the cosmological constant problem, the hierarchy problem, the nature of spacetime, the origin of the universe. Every one of the deepest unsolved problems in physics either lives at the Planck scale directly or depends, for its resolution, on what is happening there. The Planck length is, in a real sense, the address where every difficult question in physics keeps coming back to live. Part 9. The Planck length derived again. What I want to do in this part is something that I find, even now, after years of thinking about this, slightly hard to believe. I want to derive the Planck length all over again, from a completely different starting point, using none of the apparatus from the last part. No master equation, no Schwarzschild radius, no black holes at all. And I want you to watch where we land. We start from Heisenberg. Werner Heisenberg, 1927, the uncertainty principle. If you try to localize a particle to a small region of space delta x, the momentum of the particle becomes uncertain by an amount delta p, and the product delta x times delta p is at least, roughly, Planck's constant. The uncertainty principle is, in some ways, the most famous single result in 20th century physics, and it is one of the most misunderstood. It is not a statement about our instruments. It is not a statement about the particle being disturbed by the act of measurement. It is a statement about what the words position and momentum even mean for a quantum mechanical object. A particle, in quantum mechanics, does not have a sharp position and a sharp momentum independently. The state of the particle is a wave function, and the wave function can be sharply peaked in position, in which case the corresponding momentum content is spread out over a wide range of values, or sharply peaked in momentum, in which case the corresponding position content is spread out over a wide range of values. You can have one or the other, or some combination of both. You cannot have both at once, sharply. That is not a comment about technology. That is a comment about what a wave function is. There are many ways to derive the uncertainty principle. The most physical one, and the one closest to what we are doing tonight, goes like this. To know where a particle is, you have to see it. To see it, you have to scatter a photon off it. The photon carries momentum. The amount of momentum it carries depends on its wavelength. If you want to localize the particle to delta x, you need a photon with wavelength at most delta x, which means momentum at least h over delta x. When that photon scatters off the particle, it transfers some of its momentum to the particle. The particle's momentum becomes uncertain by an amount of order h over delta x. Multiply the two. Delta x times delta p is at least about Planck's constant. That is Heisenberg, derived from the act of seeing. So far, this is ordinary quantum mechanics. Now we include the new player from the last part. The probe photon has energy. Energy curves space. The photon, for the brief time it is interacting with the particle, exerts a tiny gravitational pull on the particle. We can estimate the effect. The photon has an effective mass equal to its energy divided by the speed of light squared. It pulls on the particle with a Newtonian gravitational force of order g times effective mass divided by r squared, where r is the distance between them. The pull lasts for the time it takes the photon to cross the region of the interaction, which is about r over the speed of light. From these, you can work out, with classical kinematics, how much the photon's gravity has displaced the particle. The answer, after a bit of algebra, is that the particle is displaced by an amount of order g times the photon's momentum divided by the speed of light cubed. That displacement is a new source of uncertainty in where the particle is. We can write it in terms of delta p, the photon's momentum uncertainty, which is essentially the same as the photon's momentum. The new uncertainty in position is of order g times delta p divided by the speed of light cubed. So now we have two sources of uncertainty in the position. The old Heisenberg one, which says delta x is at least about h over delta p, and a new gravitational one, which says delta x is at least about g times delta p divided by the speed of light cubed. Add them together. Delta x is at least about h over delta p plus g delta p over c cubed. This is what physicists call the generalized uncertainty principle, or GUP for short. The first term is the ordinary Heisenberg part. It shrinks as delta p grows. Push your momentum probe higher and you get better positional resolution. The second term is the gravitational correction. It grows as delta p grows. Push your momentum probe higher and the probe's own gravity blurs the position more. The two terms are pulling in opposite directions. It helps, here, to think about what the graph looks like. Put delta p on the horizontal axis, delta x on the vertical axis. The first term is a curve that comes in steeply from the upper left descending towards zero as delta p grows. The second term is a straight line, starting at zero on the left and climbing linearly upward as delta p grows. If you add them, you get a curve that comes down from the upper left, reaches a minimum somewhere in the middle, and then climbs back up to the upper right. The minimum is the smallest positional uncertainty the combined principle allows. It is the floor of the curve. There is an obvious question. Where does the combined delta x reach its minimum? The first term wants you to push delta p up. The second term wants you to push delta p down. There is, somewhere in the middle, a sweet spot. Find it the way you would find the minimum of any function. Take the derivative of the combined delta x with respect to delta p, set it to 0, solve. The math is short. Delta p squared, at the minimum, is about hc cubed divided by g. Take the square root, get delta p, substitute back into the expression for delta x. The answer, and I want you to watch this number very carefully as it comes out, is that the minimum positional uncertainty, the smallest delta x you can ever, in principle, achieve, is the square root of g times Planck's constant divided by the speed of light cubed. That is the Planck length. Again, exactly the same number we got in the last part, from the black hole argument, same scale, same order of magnitude, the same wall, derived from a completely different starting point, Heisenberg plus gravity, instead of master equation plus Schwarzschild, and arriving, with no overlap in apparatus, at the same destination. If you take only one thing from tonight, take this. When the universe gives you the same answer from two unrelated roots, it is not the roots that are telling you something, it is the universe. Physicists, when this kind of coincidence shows up, treat it as a signal. The history of 20th century physics is full of moments where two unrelated derivations met at the same number, and the meeting turned out to encode something structural about reality. The fine structure constant appears in atomic physics and in quantum electrodynamics and in the spacings of spectral lines, all separately, and the agreement is not a happy accident. The cosmological microwave background temperature matches the expansion history of the universe in two completely different observational pipelines, and the agreement is not a happy accident. The mass of the Higgs boson predicted from electroweak precision data matched the mass that was eventually measured at the LHC to within a fraction of a percent, and the agreement is not a happy accident. When the same number falls out of two unrelated calculations, that number is real. The Planck length, by this standard, is real. It is not just three constants we happen to multiply together. It is a place in the structure of physics that the structure itself keeps pointing to. There is, in fact, a third independent way to land at the Planck length, which I should mention briefly before we close this part. Take a particle of mass m, compute its reduced Compton wavelength, the wavelength a photon would have if its energy equaled the particle's rest mass energy. That is h bar over mc. Now compute its Schwarzschild radius 2gm over c squared. As you vary the mass, the Compton wavelength shrinks, while the Schwarzschild radius grows. There is one mass at which the two are equal. Set them equal, solve for the mass, and you get the Planck mass. Plug that Planck mass back into either side of the equality, and you get the Planck length. Three independent paths to the same scale: the black hole collapse path, the generalized uncertainty path, the Compton wavelength equals Schwarzschild radius path. They all meet at the same wall. The wall is real. We have triangulated it. There is one more route worth mentioning, although it goes a little outside the strict scope of tonight, because it shows up in the history of how physicists came to take the Planck length seriously as more than just a curiosity. In 1955, John Archibald Wheeler, the same Wheeler who would later coin the term black hole, who would teach Richard Feynman, who would name the participatory universe, published a paper called Geometrodynamics. In it, he imagined what spacetime might look like if you zoomed in on it at the Planck scale. Heisenberg's uncertainty principle, applied to the gravitational field itself, would mean that the geometry at very small scales would not sit still. It would fluctuate. Tiny virtual black holes would briefly appear and evaporate. Tiny wormholes would briefly link distant parts of space and then disappear. The smooth manifold of general relativity, viewed at the Planck scale, would dissolve into a turbulent, frothing structure that Wheeler called quantum foam. The picture was almost entirely speculative. Wheeler did not have a complete theory of quantum gravity. Nobody did. He had a hunch, a few rough estimates, and the willingness to say out loud that the smooth space-time everyone took for granted at large scales was probably not the right description at small ones. The quantum foam picture has, over the decades, refused to either fully crystallize into a definite prediction or fully go away. It haunts every modern quantum gravity program. The Planck length is the scale at which the foam, if it exists, would matter. The wall has 3 derivations, one speculative picture, and an enormous number of theoretical frameworks all trying, in their own languages, to describe what is on the other side of it. Whatever else we say about the Planck length, we cannot say that it is arbitrary. The universe has gone to a great deal of effort to point at the same number. Part 10. What below the Planck length even means. We have hit the wall 3 times now, from 3 different sides. All 3 routes confirm that, around the Planck length, the very act of measurement folds in on itself. Pushing further with energy creates a black hole around the region we are trying to see. Pushing further with momentum increases, instead of decreasing, the uncertainty in position. The Compton wavelength of any particle becomes smaller than its own Schwarzschild radius. The 3 effects are not, in any deep sense, different effects. They are the same fact about the universe, expressed in 3 different vocabularies. So the question becomes, and we have spent half the night earning the right to ask it cleanly, what does it mean to say that the Planck length is the smallest meaningful length? It does not mean that the universe is definitely granular at this scale. We do not actually know that. It might be, it might not be. What we know is something more subtle. We know that the operational concept of distance as something you measure by some experiment that involves probes and detectors and signals, that operational concept ceases to function at the Planck scale. You cannot, even in principle, set up an experiment whose answer is, the feature is this many sub-Planck units across. Here is the value. The experiment is not difficult. The experiment is not expensive. The experiment is impossible. Not impossible by current standards. Impossible by the same physics that makes measurement at larger scales possible. This is qualitatively different from every other limit in the history of physics. The atom looked indivisible until Rutherford. The proton looked indivisible until Slack. Every wall, in retrospect, was a door, and the next generation built better instruments and walked through. The Planck wall is not, according to physics itself, supposed to be a door. The wall is not built out of our ignorance. It is built out of the union of every theory that has worked. To remove the wall, you would have to remove the theories that built it. And the theories are general relativity and quantum mechanics, the 2 most successful theories in the history of human knowledge. Every wall has been a door, until now. Let me try to make this distinction sharper, because it matters for what the rest of the night feels like. There is a difference between a limit we have not yet figured out how to cross and a limit the structure of the world forbids in principle. Most limits in the history of science were of the first kind. We did not know how to detect neutrinos for 30 years after we predicted them, but the moment a sufficiently large tank of water was sitting underground in a mine, neutrinos were detectable. We did not know how to measure gravitational waves for a century after Einstein predicted them. But the moment LIGO came online, with the right interferometer sensitivity, gravitational waves were detectable. Both of those were Limit: we have not yet figured out how to cross problems. They yielded to time, money, and engineering. The Planck wall is in a different category. The argument is not that we currently lack the technology. The argument is that any technology that could, in principle, exist would, by the same physics that lets it exist, create a black hole at the scale it was supposed to be probing. The wall is built into the rules of the technology. So if distance is not a fundamental property of nature below this scale, then distance is not, in the deepest sense, a fundamental property of nature at all. It is something that emerges from a deeper structure, the way temperature emerges from molecular motion, or pressure emerges from collisions. Spacetime itself, this thing we casually picture as the canvas on which everything is painted, would, on this reading, be the painting. The canvas is whatever the right theory of quantum gravity turns out to describe. And quantum gravity, by construction, is something that does not live inside spacetime, because spacetime is what it is trying to explain. Think for a minute about what that means for the kind of question physics is built to answer. Throughout the history of physics, the deepest questions have, eventually, decomposed into questions about objects and the spacetime they live in. The electron is here, the proton is over there. The photon travels between them at the speed of light. All of these are statements about something: particles, fields, energies, located somewhere in a region of space, at a moment in time. Take spacetime away from the question, and the question loses, almost, its grammar. There is no where anymore. There is no when. There is something. We do not yet know how to write that something down. We do not yet know what kinds of questions are even appropriate to ask of it. I want to give the closing thought of this part to a physicist named Arkani-Hamed, who teaches at the Institute for Advanced Study in Princeton, and who has been thinking about this for a long time. He said, in a public lecture some years ago, that every time we have encountered ideas in physics that cannot even in principle be observed, we have come to see such ideas as approximate notions. However, he went on, this instance is particularly disturbing because the notion that emerges as approximate is that of spacetime itself. That sentence is what we have, all night, been walking toward. Spacetime itself, the thing that holds the chair you are sitting in, the room you are sitting in, the planet under the room, the star the planet orbits, the galaxy the star is in, the local group of galaxies, the observable universe. Spacetime itself is the approximate notion. The canvas, all the way down, ends in a question. Approximate, in this technical sense, does not mean wrong. It means a useful description of something deeper, valid in a particular regime, breaking down outside that regime. The way temperature is an approximate notion that emerges from the average kinetic energy of a large number of molecules in motion. There is no temperature inside a single molecule. There is just velocity. Temperature is what very large numbers of velocities taken together average to. Spacetime, on the Arkani-Hamed reading, is the same kind of thing. There is no spacetime at the very bottom. There are just whatever the underlying degrees of freedom are. Spacetime is what very large numbers of those degrees of freedom, taken together, average to. You are sitting on a floor that, all the way down, ends in a question. Stay there for a minute. Let the room around you hold that. There is no urgency. There has not been urgency. All night. The universe has been the way it is, with this Planck wall built into it, for the entire history of the universe. The wall has been there since slightly before the moment the universe was old enough to be measured. It will be there long after we have stopped being able to ask about it. There is something almost domestic about the wall. It is, in some quiet way, just part of where we live. Part 11. 2 doors past the wall. If the wall is real, and we are not getting past it from this side, we can still ask, very carefully, what physics on the other side of the wall might look like. Not to predict it, we do not have the experiments, but to feel out mathematically and conceptually, what kinds of structures could in principle live there. There are several serious candidates. The two with the most worked out detail, and the two most worth spending a few minutes with tonight, are string theory and loop quantum gravity. String theory says that the fundamental constituents of matter are not point particles, but one-dimensional vibrating filaments, strings with a characteristic length scale of the same order as the Planck length. Different vibrational modes of these strings correspond to different particles. An electron is a string vibrating one way. A photon is a string vibrating another way. A quark, another. The closed string vibrational mode of a particular kind automatically reproduces the spin-2 massless graviton, the carrier of gravity, in a quantum theory. Nobody put gravity into string theory by hand. Gravity falls out of the theory as soon as you write the strings down. That was the moment in the late 1970s and early 1980s when string theory stopped being a fringe topic in nuclear physics and became, abruptly, the most promising candidate framework for unifying gravity with quantum mechanics. The thing that everyone had been trying to add by hand for decades fell out of the equations without being asked. The crucial consequence for the question we have been asking is what happens when you try to probe a string at higher and higher energies. With a point particle, the master equation says higher energy gives you sharper resolution. With a string, this stops being true at the Planck scale. The string, when probed at higher energies, does not give you a sharper image of a smaller object. It gives you a larger image, because pushing in more energy excites more vibrational modes, and the effective extent of the string spreads out. The string has, in a sense, a built-in maximum sharpness. There is even a string-theoretic uncertainty principle, mathematically very similar to the goop we derived earlier, that says delta x is at least Heisenberg's term, plus another term that grows with momentum, and the minimum delta x is on the order of the string length itself. The wall is, in string theory, inside the theory. It is not a feature you run into from outside, it is built into the rules. If you read the equations of string theory carefully, you find that there is, in some sense, no notion of distance below the string length. The mathematics does not produce sensible answers there, not because the theory is incomplete, because the theory is telling you that the question is malformed. The duality between large radius and small radius, the so-called T-duality of compactified strings, actually maps small length scales onto large length scales in such a way that smaller than the string length gets reinterpreted as larger than the string length on a different topology. There is no smaller. The string length is the floor, and going below it just folds you back onto going above it. Loop quantum gravity takes a completely different route. Where string theory introduces extended objects, loop quantum gravity quantizes spacetime itself. The fundamental states of the theory are called spin networks graphs, made of nodes connected by links. Each node carries a discrete quantum of volume, each link carries a discrete quantum of area. Both are at the Planck scale. Space, on this picture, is built out of indivisible chunks, and below the Planck chunk there is no below. Not because the geometry is fuzzy, but because there are no degrees of freedom there. There is no between two adjacent Planck cells, the way there is no between two adjacent pixels on a screen. Abhay Ashtekar, in 1986, did the foundational mathematical work that made the modern loop quantum gravity program possible by rewriting general relativity in a set of variables that made the quantization tractable. Carlo Rovelli and Lee Smolin, working in the early 1990s, pushed the resulting picture into its current form. The picture is, in some ways, more conservative than string theory. It does not require extra dimensions. It does not require supersymmetry. It does not require strings. It just takes general relativity and quantizes it directly, the way Maxwell's equations get quantized to give quantum electrodynamics, and asks what falls out. What falls out is a granular structure of space at the Planck scale, in which areas and volumes come in discrete units, and the discrete units are the smallest meaningful measurements of either quantity. Loop quantum gravity also makes a striking cosmological prediction. The Big Bang singularity of classical general relativity is replaced by a big bounce, a smooth quantum geometric transition from a previously contracting phase of the universe to the expanding phase we live in now. The classical singularity disappears because the classical geometry it was a feature of does not extend below the Planck scale. There is, in loop quantum cosmology, no first moment. The universe came from somewhere, we just have no operational access to where. The classical Big Bang, where everything came from a single point of infinite density, becomes, in this picture, a description that breaks down before it gets to the origin, and the actual origin is a smooth quantum mechanical transition that the classical picture cannot resolve. Imagine a long dark corridor with two doors at the end. The first door opens onto a sea of vibrating strings. Every particle in the universe is one of them. Every force is a vibrational mode, and the doors themselves are made of strings. The strings are tiny, on the order of the Planck length, and they hum at frequencies that correspond to the masses and the charges of every particle we know. The room behind the first door is full of music. The second door opens onto a vast lattice of glowing nodes, connected by glowing links, each node a quantum of space, each link a quantum of area, with no in-between anywhere. The room behind the second door is full of geometry. Both doors say the same thing in different languages. This is what the wall looks like from the other side. The listener does not have to choose. The listener has, in fact, no way to choose, because no experiment we can build right now distinguishes the two pictures. We can only stand at the end of the corridor and look. There are other doors, and they are worth at least mentioning. Causal dynamical triangulations is a program run primarily by Jan Ambjörn, Jerzy Jurkovic, and Renate Loll, in which spacetime is built up numerically out of small, four-dimensional simplices of approximately Planck scale edge length. The remarkable thing about causal dynamical triangulations is that, at large scales, the simulations produce something that looks like the smooth four-dimensional spacetime of general relativity, but at small scales, the effective dimension of the spacetime drops to about 2. The geometry has a fractal quality near the Planck scale. Spacetime, in other words, may not even be four-dimensional at the bottom. It may behave more like a two-dimensional structure that only looks four-dimensional when you stand far enough back to average over many Planck cells. Asymptotic safety is another door, primarily a program of Steven Weinberg and a community that has grown up around his 1976 paper on the subject. The idea here is that gravity might be a perfectly well-defined quantum field theory, all the way down to and below the Planck scale, provided certain coupling constants, Newton's G, the cosmological constant, and a handful of higher derivative couplings flow to a non-trivial fixed point under the renormalization group. If they do, gravity is consistent at all energies, and the Planck length appears as a crossover scale where the theory transitions from its low-energy behavior to its high-energy fixed-point behavior. The wall, on this reading, is not a wall at all. It is a transition zone. Causal sets, a program primarily associated with Raphael Sorkin, takes spacetime to be a discrete set of events with a partial order encoding causal relations. The set is sprinkled randomly at a density set by the Planck scale, and the continuum spacetime of general relativity emerges as an average description over very large numbers of these discrete events. The Planck length, here, is the average spacing between adjacent causal set elements. The holographic principle, a deep result from black hole thermodynamics in the early 1990s due to Gerard Hooft and Leonard Susskind, says that the information content of any region of space is bounded by the area of its enclosing surface, measured in Planck units. The Bekenstein-Hawking entropy formula makes this precise for black holes. The entropy of a black hole is its horizon area divided by 4 Planck areas. The Planck length on this reading is the pixel size of the universe's information encoding. Spacetime is, in some sense, a hologram projected from a lower dimensional surface, and the Planck length is the resolution of the projection. There are other doors. The doors all open onto subtly different rooms. The interesting feature is that in essentially every door, the Planck length appears not as a barrier you crash into, but as a basic structural element of the theory. The theories build the Planck cutoff into themselves. They do not run into it from outside. If you ever wanted a clearer signal that the Planck length is something real, something the universe is telling us about itself, rather than something we accidentally derived from 3 constants, that is the signal. Every serious theory of what is beyond it contains it. The Planck length is the one number that every otherwise incompatible program of quantum gravity agrees on. They cannot agree on what spacetime is. They cannot agree on whether it has extra dimensions. They cannot agree on whether it is fundamental at all. But they all agree, in their own languages, that the Planck length is where the current picture stops working and the new picture takes over. Whatever the right answer turns out to be, the right answer has the Planck length built into it. There is one more striking convergence worth lingering on. Several of these programs, when they compute the effective dimension of spacetime at very small scales, find the same surprising result. The dimension drops. At everyday scales, spacetime is 4-dimensional, 3 of space, 1 of time. At Planck scales, in causal dynamical triangulations, in some loop quantum gravity calculations, in certain asymptotic safety calculations, in Horava-Lifshitz gravity, the effective dimension, a random walker on the geometry, would experience drops to about 2. The geometry, in some sense, is fractal at the bottom. It folds, it compactifies, it loses degrees of freedom. The 4-dimensional manifold we live in, on this collective picture, is a coarse-grained description that emerges only at scales much larger than the Planck length. Underneath, the structure is not 4-dimensional at all. It is something stranger and lower dimensional. The convergence does not on its own prove anything. None of these programs is complete, but the fact that 4 or 5 independent attempts to describe Planck scale physics keep stumbling onto the same low-dimensional behavior is the kind of thing that physicists notice. It suggests, gently, that whatever the right answer turns out to be, it will involve a spacetime that is not what it looks like at human scales. The 4-dimensional world we walk around in might be the surface texture of something more compact, more folded, more strange, all the way down. Part 12. The wall is part of the building. We started, all those hours ago, with a child's question. What happens if you keep cutting? The answer the universe has given us, after 400 years of looking, after every microscope ever built, after Democritus and Hooke and Leeuwenhoek, after Davison and Germer, after Friedman and Kendall and Taylor, after the LHC and the discovery of the Higgs, after Einstein and Heisenberg and Schwarzschild, after Wheeler and Ashtekar and Arkani-Hamed, the answer the universe has given us is that yes, there is a flaw. It is at about 1.6 times 10 to the negative 35th meters. It has a name, the Planck length. We can compute it, we can derive it 3 different ways from 3 different starting points. We can build whole frameworks of quantum gravity around it. We know an enormous amount about where it lives, and we cannot stand on it. The wall is not a problem we can engineer around. I said that earlier in the night, almost lightly, in the middle of talking about accelerators a few % of a galaxy across. It comes back now with the full weight of everything we have walked through. The accelerator argument was the easy version of the sentence. The hard version is the gup, The hard version is the black hole. The hard version is the convergence of every quantum gravity program ever proposed onto the same scale. The wall is not something we have, with bad luck, failed to engineer around. The wall is what the rules of physics have engineered into the building. Every wall has been a door, until now. That is the second sentence I asked you to hold on to. We do not, of course, know for sure that this wall is permanent. New theories might come. New experiments might be possible in ways nobody currently sees how to set up. The history of physics has been very humbling to anyone who said, "This is the end." But the difference between the Planck wall and every previous wall is that the previous walls were built out of our ignorance, and ignorance is the kind of thing that yields to better instruments and braver thinking. The Planck wall is built out of the union of the theories themselves. To remove the wall, we would have to remove the theories. And the theories, quantum mechanics on one side, general relativity on the other, are the most experimentally successful frameworks in the history of human knowledge. They do not give up their walls cheaply. You are sitting in a chair. The chair is made of something. The something is made of cells, of molecules, of atoms. The atoms are made of quarks and electrons. The quarks and electrons are excitations of fields. The fields live in spacetime. And spacetime, all the way down, ends in a question. Not a question physicists have not yet answered. A question physicists have, as a community, come to suspect cannot in principle be answered from inside the spacetime the question lives in. That is, in some quiet and very ordinary way, the strangest sentence about the chair you are sitting in that I know how to say to you. What you are sitting on, all the way down, ends in a question physics cannot name. I do not, on nights like this, find that a frightening thought. I find it a beautiful one. Every century of physics has been the slow process of finding out that the world is built on something stranger than the world before it knew. The atom was strange. The quark was stranger. The Planck length is the strangest. There is, in this kind of strangeness, no terror. There is only the long, slow, calm realization that the building is not finished, that the foundations are not where you thought they were, and that you are inside a structure whose architecture is, at the deepest level, still being worked out. The architects, in this case, are not human. The architects are the laws of physics themselves, and they have been working on the foundation longer than there has been a foundation to work on. The foundation predates us, and the foundation will outlast us, and the foundation, from our angle, ends in a wall we did not build. The wall is part of the building. If you keep asking, very gently, what is underneath the wall, you will keep getting answers that are not quite answers. Spacetime is approximate. Distance is emergent. The canvas is the painting. The corridor leads to two doors, and you cannot choose between them. The universe is built, at its base, out of something that we, here, in 19 of the 21st century, do not yet know how to write down. And nobody is going to write it down by next week, or next year, or possibly in the lifetime of anyone reading this. The wall is patient. The wall has been there as long as physics has been there. The wall, in fact, has been there since the first Planck time after the Big Bang, which is to say since slightly before the universe was old enough to be measured at all. Let me try, in the closing minutes, to say one more thing about what the wall means for the listener, personally, sitting in a chair or lying somewhere comfortable while this video plays. The Planck length is not, for any practical purpose, a thing you have to think about. The chair will hold. The floor will hold. The atoms in the room will, with statistical certainty, continue to behave the way atoms have always behaved. The fact that those atoms are made of quarks and electrons, that are excitations of fields living in something the deepest theories of physics cannot fully describe that fact, does not, in any operational sense, change your Tuesday. The Tuesday is exactly the same with the Planck wall as without it. What changes, if you let it, is the felt sense of what Tuesday is happening on top of. The felt sense of how deep the floor goes before the foundation runs out. The felt sense that, somewhere very far underneath you, the building is unfinished, and the people who are working on it have not yet handed the keys to anyone. For some people, that felt sense is unsettling. For others, and I suspect for most people who have spent any real time with these ideas, it is the opposite. It is settling. The world is too big and too strange to fit inside any one person's head, and there is a particular kind of quiet that comes from knowing this, from feeling it as a present fact rather than as an abstract argument. The Planck wall is the universe gently reminding you that the world is bigger than its appearance, that the foundation is deeper than it looks, and that the people who study it for a living, who have been at it the longest, are still mostly standing around at the bottom of the staircase, looking at the floorboards, and quietly admitting that nobody knows yet what the floor is made of. There is also, if you let it land, a kind of company in the thought. You are not alone in standing on the unfinished foundation. Every other conscious thing in this universe is on the same floor. Every person you have ever loved is sitting on the same Planck wall, whether they know it or not. Every animal on the planet, every star in the sky, every photon currently in flight from the moment of the Big Bang, all of them are riding on the same provisional spacetime that nobody has yet fully described. The wall is not a personal feature of your own situation. It is a feature of the universe as a whole. The cosmic microwave background, that ancient light from when the universe was 380,000 years old, is still in flight tonight, and its propagation is governed by the same general relativity and the same quantum mechanics that produce the wall. The photons are travelling across space-time, whose deepest structure no one can describe. The photons do not seem to mind. They have been travelling for 13.8 billion years without incident. Whatever the foundation is made of, it has been good enough to carry every photon, every electron, every atom, every molecule, every star, and every life, and every conversation, for the entire history of the universe so far. The wall does not interfere with any of that. It just sits there, quietly, underneath everything, refusing to be looked at directly. There is, in the steadiness of that refusal, something that almost rhymes with the steadiness of a held breath. The wall has not changed in 13 billion years. The wall is not going to change tonight. The wall will, in some real sense, outlast every human institution, every human language, every human civilization. The wall is, in this very particular and very gentle sense, one of the most patient features of reality. It has nothing to prove. It has nothing to do. It just sits there, 20 orders of magnitude below the proton, waiting for the equations of physics to be rewritten in a way that lets us speak about it properly, however many centuries that takes. You can fall asleep now, if you like. There is no rush. Tomorrow there will still be a floor under your feet, and the floor will still be made of atoms, and the atoms will still be made of quarks and electrons, and the quarks and electrons will still be excitations of fields, and the fields will still live in something current physics cannot quite describe. None of that is going to change in the night. The wall is part of the building, and the building is the place you live, and the place you live is, quietly, much stranger than you thought when the night started. The strangers down at the foundation are not enemies. They are working. They have been working a long time. They will keep working. They are not in a hurry. There is, in their patience, a kind of company. Stay there. The lights are low. The numbers are spelled out. The rule is gentle. And there is, all the way down, still no floor. There is, instead, a wall patient, ancient, built into the foundations of every successful theory the species has ever produced, and the wall, in its own quiet way, is keeping you company tonight as well. It is not a thing you have to solve. It is not a problem you have to fix. It is simply what the very bottom of the world looks like from where you are right now, sitting where you are, breathing as you are, present to a universe that is much larger than what you can see from inside it. The wall has always been there. The wall will always be there. The wall is, in some quiet and very ordinary way, the part of the room you can rest against without ever quite touching.